Hello. Today we're gonna talk about what we as game developers could learn from the other disciplines of front-end development and basically what advancements have been made in the field for the last 10 years. So let's take a look around. Games are user-facing products, and such products are known as front-end software. So if you're not familiar with the term, basically there's front-end software and the back-end software. And you could think of it as, if you have your store, there's the front end of the store, the part the customers come in and they interact and they see all the goods laid out and, the prices and everything. And then there's the back end of the store, which is basically a big storage room with all of the inventory. So it's the part that regular customers do not usually see. So games are the things that the gamers see. And there are other front-end software products as well. We have websites, we have mobile applications that the people interact with, we have desktop applications as well. And can we take a look at them and learn anything from those types of applications? Well, let's take a look at the evolution of the front-end development. If we take a look at websites, they used to be pretty static back in the day, like way back in the day, like 2000s, when the web was kind of growing. And then around 2006, jQuery got released, and it was the first popular library to allow you to add interactivity into your website, into making things move and, click and fold out and toggle and stuff like that. The first website framework was like Angular 1, released in 2010, and it kind of built upon the imperative paradigm. Then a couple of other versions and frameworks have followed, Angular 2 in 2016, React in 2014, Vue 2014, and they moved towards imperative plus functional paradigm. For the mobile applications, specifically Android, we also see this evolution. We had XML-based layouts in the original Android, and just recently, 2021, Jetpack Compose was released, which is a lot more functional and declarative. Same in iOS development. UIKit, released in 2015, was imperative, which was transformed into SwiftUI in 2019, which is functional. And things like React Native or Flutter, released at 2015 and 17, respectively, they are functional by default. So the pattern that we see here is that these front-end development technologies that have started with kind of imperative programming have moved towards declarative functional programming. And there's a good reason for that. Imperative programming is very hard to get right at a big scale. And I guess we need to kind of step back a bit and talk about what actually is a programming paradigm. And it is a way we express the steps of our program and the steps of the program takes to achieve the desired results. So basically, it is things that we want our program to do. And there are multiple ways to express those things. If we're talking about imperative programming, that is all about you have some data and then you have some statements that change that data. And functional programming is about having some data, but instead of statements, you have some expressions that transform that data. And let's take a look at a couple of examples that should help understand this a bit better. So let's say we want to get the total age of all people in the room. If we would implement this in an imperative programming paradigm using C#, it would look like something like this. So we start with a statement saying the total age is 0. Then there's another statement that says, let's go for every person. Yet another statement that says, please add this person's age to the total age. And finally, another statement that says, let's return this total age. So as you can see, there's different statements. The program is composed out of statements that, in our case, we have this total age here. This is some data, and it mutates that data, changes that data using statements. Now, if we look at functional instructions, they're a bit different. Basically, we have this list of people, and then we say, from every person, select that person's age, and then just sum everything. So it is kind of more declarative. It is more something closer than what you would say, how do you compute the age of all people? Well, you just sum every person's age. It is something more like English instead of being steps for the computer. Of course, behind the scenes, we still have these steps because the computers are still imperative and we have to tell them how to do things step by step. But as programmers, we can express ourselves in this more clear fashion. So let's take at another example. Let's say we want to make a cake, and the recipe is I don't bake cakes, so this might be totally off the charts. Don't judge me for this. But let's say we want to make a cake by taking butter, flour, eggs, sugar, and baking powder. We have to mix all of them in the bowl, and then we put that into the oven for 15 minutes at 200 degrees Celsius. So that, the imperative instructions might look something like this. We first create a bowl, then we add a bunch of ingredients into it, then we state that the bowl should be mixed. Then we create an oven, we put the bowl into the oven, we set the temperature, and then we say bake for 15 minutes. And then we take out the bowl out of the oven and we say this is cake. Well, it's a synthetic example, but it's just to kind of illustrate the point. And if we take a look at functional instructions for the same problem, you declare that the bowl has there's a bowl and it has these ingredients inside. And then you say mix, and after you mix that, you get a different thing. You get a mixed bowl. So there's a transformation happening from the bowl to the mixed bowl. And then you call this function called oven bake. You give it a bowl, you specify the parameters, and you get out the cake. Again, another transformation. So let's compare these two. In imperative, the primary goal is mutation. You have some data and then you change that data. In functional, the primary goal is transformation. You have some data and then you transform that data into another data. So, if keep baking the cake, in imperative you had like a bowl, and then you invoke a method mix and it changes the bowl. In functional, when you call the method mix, then it transforms the bowl from a regular bowl into a mixed bowl. And these things in imperative are achieved with statements, while in functional paradigm they are achieved with expressions. And the code in imperative paradigm is about how to do things, like the exact step-by-step instructions how to do things. And in functional, it's more about declaring what do you want to do, as seen in the people age counting example. So where does the functional programming shine? One of the things that functional programming is great is composability, because functions are essentially the primitive primary composability thing. So you can always take a function from A to B and a function from B to C and compose them into function from A to C, which might be a bit too abstract. So let's take a look at it like this. So if we have a function from bowl to mixed bowl, which is A to B, and then another function from mixed bowl to cake from B to C, you can see that we can just kind of add them together like pipes, connect them together, and then you just get this composed pipe, where what you give it a bowl and it produces you a cake. So that's very easy to compose. With functional programming, there's kind of no more runtime exceptions, or at least a lot less runtime exceptions, because you have these immutable data structures, and you can make sure that these immutable data structures are not constructible with invalid state. So if you have invalid state, it's just impossible to create such a data structure. And if you can't create it, then you can't have any errors with the thing. Well, you have compilation errors, but not runtime errors. So for example, one of the things that you can do is, if you have immutable data structures, you can distinguish between a data structure which is potentially empty and a data structure which is guaranteed non-empty. And if you have this data structure, if you take a random element for the potentially empty collection, you must have return something optional, because it might be empty and there might not be any elements in it. But if you have something that that it is non-empty, you can always safely return the element, because there will at least be one element. And immutability really helps here, because after you construct this collection, there's no way for it to change, and therefore this knowledge that you have will not become invalid, which can happen with a mutable data collection. So if you just have a reference to a list, anybody at any time can add or remove elements to that list, so you don't really know whether it holds a certain amount of elements or not. Functional programming also allows us to do local reasoning. And basically what that means is, when you're doing functional programming, it's very easy to reason about, because the functions that you work on, they do not care about the origins of the values they're getting. So, you just get some values and you don't really have to know where those values come from. There's no context. You just know that, I'm getting these values and this is what I'm gonna do with them. We will cover this in the rest of the videos in more detail. Tests are also easy with functional programming. Basically, if you adhere to purely functional programming paradigm, everything is just a pure function, and there's no need for mocks or other brittle techniques to change the internal state of objects. You just pass some parameters in, you get something out. It's very easy to write a test for that. One thing that is very useful in game programming is no more dirty checking in UI. So basically, functional programming is a great tool to solve this problem of how do you make sure that your user interface does not desynchronize from your data. So there's plenty of games that I've played where it says you have like 5 workers, and then you try to build something and then you get an error saying, oh, not enough workers. So functional programming is a great way to do that, to fix this thing. And again, we're gonna get into more detail at a later video, but essentially the really great thing is that immutable data structures make change propagation very efficient. So to know whether something actually changed or not, we can just do a reference check. And if it's the same reference because the data structure is immutable, well, you know that it hasn't changed because it's impossible for it to change. Although nothing is perfect. With functional programming, the performance is worse in a small scale compared to the imperative code. So if you have some algorithm that you want to do, often it is way better to write that in imperative paradigm than it is in functional paradigm, because the functional paradigm needs to recreate new objects and new data structures when it transforms them from one to another, whereas imperative can just change things in place, and that's faster. And also, usually people already know how to do imperative paradigm and object-oriented programming, and they are not as familiar with functional paradigm. So, often it is the case that it needs learning and it needs teaching. But I guess that's why you're here, right? So with all that in mind, let's do a comparison again. So we've seen these three. And continuing, basically, composition in imperative paradigm is about data. So, it's either via inheritance or more preferably by composition, where you put objects or data structures within other data structures. Whereas in functional paradigm, composition is about functions and connecting these functions into bigger functions. Usually the imperative paradigm has less pressure on garbage collector because it doesn't allocate as many objects. Whereas in a functional paradigm, if not done right, you can easily put immense pressure on the garbage collector. So you have to have that in mind. This is why when writing games ourselves, things that run in the gameplay loop are often imperative, mostly imperative, with some functional sprinkles, but just because you can't really allocate garbage there. And imperative offers maximal local performance. So, in a small scale, in a scope of a class or two, you can get the maximal performance. But with a functional paradigm, it kind of limits you, and those limitations free you to apply certain optimizations on a large scale, on a scale of an application. With imperative paradigm, it has been my experience that often large scale software, like hundreds of thousands of lines of code, becomes hard to comprehend, while applying the functional paradigm, it's still easy to comprehend. So what we do in our games, and what I will suggest to do in this course, is this architecture. Applying imperative paradigm in the small scale. So for things like gameplay code, for things where you need the maximum performance, where the code is fairly isolated and easy to understand. And then applying the functional paradigm in the larger scale for things like application architecture and user interface code, where there is no need usually for the maximum performance, but things are interconnected and complex, and there's a large need for clarity. So such an architecture is perfect for writing and maintaining a large-scale long-term projects that span 2 years, 3 years, or more. So what's our next stop? Well, to know how to use this functional paradigm, we first have to learn the basic blocks of the functional paradigm. And for that, I'll see you in the next video.